Yeah, it's showing that it's live stream. Okay, I'll open the YouTube also so I can see.
Mm.
Did you start the recording?
No.
Yeah, it's showing the live. Yeah, it's showing live here.
Okay.
Hmm. Can you start the recording as well?
I'll start it after he joins. That's okay, right?
Yeah, that's okay.
Yeah, after he joins this YouTube, we cannot talk, right?
Yes. If you will stop, then it will don't go live again.
Um,
Hmm.
okay, I'll unmute and I'll wait for him.
Meanwhile, you can share the screen or do some. Hmm.
Why?
Just try. It is showing the clear. It's not showing the unwanted thing. Did you try the share screen?
Mm, yeah, I'm able to share. You can see, right?
Yes, yes, I can see. Good. Can you disable the annotations for the participants?
But I mean, all these things he has to do now. Where is
Yes.
it? Annotations.
Did you share the screen?
Yeah, I
So,
did.
why it is not locating? Uh, you can click here that you are sharing screen. You can see here, there. No, no, you are sharing
Okay,
your
okay.
screen here. You can see there. There is a three dot.
Disable annotation for others. I think I'm not touching anything now. Disable annotation for others. Now?
Yes, yes, you can disable the annotation for others. Yeah, I cannot see the annotation. Okay,
Okay.
fine.
This I should do or he should do?
When he will share the screen, then he have to do.
He should do, right?
Hmm.
Okay. Then I will enable annotation now and stop share. So now only thing is recording, nothing else, right?
Yes.
Yeah. Okay then. Be here. We will see once he joins.
Okay.
Hello.
Hello, Professor. Thanks. Thank you for joining.
Good. So good. I think this is working. Would you like me to share my slides or something so that you can
Yes,
check?
yes. I'll give you the co-host access and then you can share.
Very good.
Yes, you can try sharing.
Can you see this?
Yes, I can.
Cool. Oh, share. Good now. Sounds good. Cool. Shall we? I guess we wait for a little while for people to join and things like that, right?
Yes, we'll start at 5:30, so you can.
So does everyone join online, or some folks will be in a seminar room kind of thing, or how does this work?
No, everyone join online if it's an online talk.
Very good. Very good.
Usually
Sounds
it's hybrid talk. So
I see. Good. Okay. I'll wait for later. Thank you.
yes. shall we start, Professor?
We can start.
I'll introduce you and then you can start.
Perfect.
Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBC CPS IASC. It's my pleasure to introduce today's speaker, Professor Srinivas Shakkottai. He will be speaking on CONGO, Compressive Online Gradient Optimization. Professor Shakkottai received his PhD in Electrical and Computer Engineering from the University of Illinois in 2007, followed by a postdoctoral position in Management Science and Engineering at Stanford University. He joined Texas A&M University in 2008, where he is currently a professor in the Department of Electrical and Computer Engineering and holds a courtesy appointment in the Department of Computer Science and Engineering. His research interests include wireless networks, reinforcement learning, caching and content distribution, multi-agent learning and game theory, network markets, and data analytics. He co-directs the Learning and Emerging Network Systems Laboratory and the RELIS Spectrum Innovation Laboratory at Texas A&M University. He has served as an associate editor of the IEEE ACM Transactions on Networking and the IEEE Transactions on Wireless Communications. He's a recipient of Defense Threat Reduction Agency Young Investigator Award and the National Science Foundation Career Award, as well as research awards from Cisco and Google. His papers have received honors at venues such as ACM Mobihawk, ACM E-Energy, and ICLR. At Texas A&M, he has received several distinctions, including the Outstanding Professor Award, the Select Young Faculty Fellowship, the Engineering Genesis Award, and the Deans of Engineering Excellence Award. Over to you, Professor.
Thank you so much for the kind introduction, and thank you all for being here. It's probably 5:30 p.m. your time, so it's fairly late. So thank you for staying after work and all that kind of thing. So today's talk, I'm going to talk about CONGO, which is Compressive Online Gradient Optimization. But before I get started, I want to do a little bit of general advertising on what we do in the lab. So I have a few slides which basically show some videos on the kinds of things we are doing in the lab. So let me just share that first. So yeah, I'll start here. It'll take 5 minutes. So continue to share. Very good. So my name is Srinivas Shakkottai, as was mentioned, and my lab is called the Learning and Emerging Network Systems Laboratory. And it is co-directed by Professor Dilip Kalathil, who's been my colleague for many years. So essentially what we do is connected intelligent systems, sensing, sense, communicate, compute, control. That's the kind of thing. So in other words, we have distributed sensing, 5G or next G communication, which then leads to distributed compute and ultimately leads to some kind of decision making. So essentially the key areas that we're interested in is next G wireless distributed compute system, autonomous robotics, a whole bunch of work in machine learning, and robustness of this AI/ML models. In other words, we work on a variety of use cases of, as I said, distributed compute connected through networks with some ultimate decision making. Right. So to give a few examples of the kinds of things we do, we typically will have a physical system of some kind which has sensing. We have a communication system connecting everything together, a whole bunch of distributed compute. This might be edge compute, cloud compute, etc. And everything is glued together with machine learning typically at this point. So we're looking at distributed algorithm design with certain provable properties. Oftentimes nowadays it does take the form of ML-based algorithms, things like reinforcement learning. And today I'm going to talk about compressive sensing, particularly with for online learning and so on. So essentially the idea is the physical system generates samples, the communication system carries these samples to the compute system, which then is able to produce decisions. Now the decision making is kind of multifold. First, the ML might be used to modify or control the communication system itself. The ML might be used to modify the compute system and runs on the compute system as well. And of course, jointly the communication and compute provide the decisions for physical systems. So oftentimes the motivation is connected autonomy, where you've got these distributed robots here connected through networks with compute all over the place. Roughly speaking, that is the general scheme of things. A few videos on on the kinds of things we're doing. So on the left side, you see the kinds of robots and kind of equipment that we work with. Phased array antennas, software-defined radios on the bottom left over here. Then basically, let me switch to laser pointer. So here, this is essentially a software-defined radio sitting on one of our workstations. This is a small robot carrying a phased array unit, which is both mechanically tiltable and electronically steerable. Robots of different kinds. And oftentimes we'll take these and switch it over to much more large-scale systems. I collaborate with folks. We have certain larger robots like this Warthog robot and a few other locations where we work at with more at-scale kind of experiments and developments. So a couple of examples. I guess this is a networking seminar, so I thought this video might be interesting to folks. One thing which we've built, which we've been collaborating actually with Professor Anurag Kumar as well, is on a so-called EdgeRIC, which is real-time cellular control. So the idea is basically that you're trying to capture telemetry information directly from a radio and modify things like the scheduling algorithm, the physical layer, that kind of thing. So in other words, we've built a system which is able to capture these artifacts at very, very fine time scale. It takes about 50 microsecond or thereabout for communication with EdgeRIC. RIC stands for RAN Intelligent or Radio Access Network Intelligent Controller. So it grabs this info and sends the control back. It can also take application state. And so essentially the idea is we are able to do extremely low level optimizations very, very quickly, right? We call these micro apps, right? This is an open source code base. So if you're interested in these kinds of things, contact me. Here's an example of the kinds of things EdgeRIC can do for you. So here we're showing with two SDRs, right? These are two software-defined radios. This side is working like a 5G base station, and those are the two UEs. This is working with an open source code base, which is called SRS RAN, which can run on real radios, real means carrier grade radios, as well as connect real phones and so on. With EdgeRIC, the idea is that essentially you can drop in new ML models whenever you want. So in this particular case, you notice there's a max weight scheduler. This is the throughput. You give half the resources to each user, it drops the throughput. Now we're going to start dropping ML models. The first ML model is kind of so its throughput falls. So essentially, good thing about this, you can update in runtime. As I drop in new models, it starts using them for scheduling. So here you notice it's improved already, and it's going to go still further up. So you notice that the models are able to kind of adapt in real time. We can use this for a variety of use cases. This particular one has to do with this idea of driving a robot over the network, in which the robot, the network is cognizant of the robot's needs. So essentially, the scheduler can adapt. In this particular example, essentially, when we load up the system on the top left, the throughput has gone up, and you see this is starting to lag. This is video and LiDAR feeds, which are coming from the robot. You notice the robot moves, nothing happens here for a while. Right now it moved. So essentially, on the other hand, if you have a scheduler which is cognizant of these needs, you could argue it's a kind of age of information cognizant kind of scheduler. It's basically able to manage to do this in spite of the higher throughput. So you notice now it's not lagging. These are the kinds of things we do. I don't want to belabor the point. We work on, for example, phased array antennas. You see that robot has a phased array antenna. And essentially, the idea here is showing that we can do beam steering. Notice that the kind of SINR at the robot has fallen. If you choose the right beam, it'll suddenly pick up, right? We'll see that in just a second or two, right? So effectively, there's a pan tilt unit on the robot, so it can physically change, and there's electronic steering. Now the SINR suddenly goes up. Other things that we do are kind of with various robots. Here, for example, on the top left is a telepresence robot in which we're doing imitation learning. We ran this robot like 50 times around the lab, and now it's able to learn how to do it. So robust imitation learning, fine-tuning these models. On the bottom right, you see a pick and place robot which managed to place it. These are roughly the kinds of things that we do in the Lens lab, right? So I just wanted to give a little bit of overview on that. And if you're interested in anything that you just saw, do reach out, and we can talk further. Now, that said, I just want to switch over to my actual talk, which is much more in the algorithm domain, right? So as was mentioned, can you still see my screen? Good?
Yes.
Good, perfect. So as was mentioned, background-wise, a good deal of what we do and what I've been doing is on the algorithmic side. In this case, it's on online learning, right? So in this case, online learning meets compressive sensing is the theme of this. So the folks I work, this appeared actually in ICLR this year, International Conference on Learning Representations. This jointly with a bunch of folks. Jeremy is a PhD student of mine. Pratik was a master's student who's graduated. Divyanshu is Aditya Akela student from UT Austin. And Dheeraj is actually, he was at INRIA when he did this. He's spending some time right now at IISc. And afterwards, he's on the job market. Whether he will join in India or abroad is an interesting question. So these are the folks that we worked with. And this particular problem is motivated by the fact that many distributed applications are essentially resource allocation problems, compute or communication resource allocation, spectrum or CPU cycles. In this particular case, we're interested in allocating CPU cycles. It was more broadly CPU, GPU, memory, these kinds of things, right? Dynamic traffic requests. Now, so essentially, many of these follow the so-called microservices architecture, which means essentially you containerize your application, and each container runs a virtual service, and the kind of overall application consists of jobs going from service to service to service, right? So in other words, for example, some of the benchmarks that we looked at were, for example, if you have a social network, right? So there might be a compose and a post kind of job requests coming in which you're kind of composing the actual social media post. You're putting pictures, you're writing stuff, and then you click OK. It has to go there. It has to pull various media from different photographs and other things you might have, and ultimately wind up at a location where other people can access it. So in other words, many of these services, database services, the kind of front-end services, etc., will all go into servicing your job, right? So you can think of this as job jumps from queue to queue to queue to queue, and each queue does a little bit of work on that job and moves on. So essentially, these kinds of things fit this online convex optimization framework because, as we'll see, essentially, the kind of metrics of interest, latency, performance, etc., are often follow convex functions. And of course, you're doing such allocations in an online manner. This is the kind of motivation that I just mentioned. On the left side here is actual, this is a microservices type application. You notice it says microservice and Jaeger client. So effectively, the Jaeger client is how we are measuring the microservice performance. But what I'm pointing out is when a job comes along, it'll go to microservice 1 and then 2, or maybe something will happen in another one, etc. Ultimately, it'll go through a variety of microservices and be complete. So we took some measurements on these benchmark applications to see if indeed, because most queuing systems you expect, as the load goes up, the latency will go up for a fixed amount of resources. And we found that indeed it is convex increasing in this case. And similarly, with respect to CPU allocation, if you take a particular microservice, of course, all the others are not bottlenecked, then essentially as you give more and more CPU, the latency does go down, and it does go down in a convex manner. You notice the shape looks interesting, right? So in other words, we have these kind of convex objective functions. Supposing you're trying to minimize the total latency, each of these is seeing such a latency function, but I don't know the function itself. I can't bench test every single container in the world to get this curve out of it, right? Also, the combination of these containers means that some of them will be bottlenecks for the current load profile. By current load profile, I mean, it's not like there's only one type of job that this application is dealing with. It'll deal with a variety of jobs. In the social media thing, which I mentioned, people are composing, people are drawing stuff, people are posting media, they're doing a variety of jobs. So each type of job will go through some bunch of microservices, and the load on the microservices, therefore, will depend on this kind of load profile, which we don't know. So what do we do? So when you look at these kinds of OCO style problems, effectively, what you're really trying to do is the problem is that you're over time, this should have been little t, over a certain period of time, 1 through capital T, you've got a function which is changing every single time. So in other words, what we've got here You notice it says ft of xt, so it basically means the function is changing with time, and xt is the decision variable of interest. So essentially the point is that what you would like to do is minimize this, right? I mean, that is the kind of figure of merit. You want to minimize the total cost, but what you're ending up doing is something, right? And so essentially the regret that you suffer is what you ended up doing versus what you wished you could have done, right? You wanted to minimize the cost, but you ended up getting this cost. And the regret is the largest possible value that this could take over the class of f's, right? So in other words, this is an adversarial setting in the sense that there is no particular distribution from which these f's. In our case, if you go back here, the f is basically like these, right? We don't know what the functions are. We don't know what the loads are. You could argue that the containers didn't change, so the functions didn't change, which might well be true, but then the loads could change. And indeed, when we do our bench applications, or when we run our benchmark applications, which I'll show you in about half an hour or 45 minutes, is basically, you'll see that what we do is we change the loads using a somewhat realistic load profile. So in other words, the excess will change in our case over time, and there will be some arbitrary sequence of excess, which I don't know, the loads that show up in my system. So in other words, the only information that we have about the state in a practical system is what we can obtain from sampling, right? In other words, I can measure, I can send particular jobs through the system, is exactly what we do, and we can measure the end-to-end latency. Again, coming back to this diagram, that's what this Jaeger client does. So you send basically jobs through the system, and you can measure the latency in an end-to-end manner. You can see how long the jobs took to complete. So you'll send like 10 jobs, 20 jobs, etc., as measurement jobs to just see what the end-to-end latency is. So if you want to try to now use a kind of gradient descent type regime on this, you need to know the gradient of this function. That is, you need to know the gradient of f, right? But essentially here is a sequence of what really is going on. So there is going to be some load and perhaps parameters. So in other words, in this x, we're saying these are both the load parameters, which I cannot touch, as well as the CPU parameters, which I can touch. In other words, think of this cost function f as depending both on the load and the resources. Again, this is true here because you notice with load it is going convex increasing, and with CPU it is convex decreasing. The load I cannot touch. It is what nature gives me. But CPU allocation I can. So in this particular example, what we do is we basically run it through Kubernetes, and Kubernetes is able to basically allocate amount of CPU per container. So in other words, I can do this. I'm kind of grouping all these variables. It's a whole vector of variables times containers, right? So I'm grouping all of that into this vector x here, right? Now the point is this is going to be extremely high dimensional because you notice in this example I've shown only about 6 containers, but many of the benchmark applications will have like 40-50 containers. Even much larger applications exist. So in other words, we're basically saying this is a very large dimensional x, some parameters which are not under my control, the load part of it, and the allocation part of it is under my control. So that's the general setup. Okay. Incidentally, do stop me. I cannot see you actually, so anytime you want to just stop me, because I'm going to give an overview and talk about algorithms and so on. There is some notation involved. So if you get lost or you have any questions, just stop me whenever you feel like. Right. So here is what is going on. Therefore, so there is this x, which some of which the parameters which I set and some which nature gives me. The adversary. That's what I mean by saying the adversary plays f1. Some function happens, right? There is going to be a cost. For what follows, I'm going to kind of at least notationally, the function will be given by the adversary while x is for me to choose, right? It's just for simplicity. But in the actual system, the f is also fixed. It's really the load part of the x which the adversary chooses and the allocation part of the x that I get to choose. But that's just a subtlety. Just think of it now as the adversary plays the function while I play the x, right? So now what I need to do is I need to find the gradient, right? So basically the algorithm, which is what we have to design, is going to hopefully be able to take several samples of the f of x, right? It's for me to choose x, as I said. So essentially what I can do, right, is choose a variety of x's, variety of allocations to see how the function changes for each of these. Now, the inherent assumption here is the f is changing slow enough. Like you notice out here, it looks like the f changes every single time instance, f of t equals 1 to t. Here what I'm saying is, this is the fact, but between these two changes in f, I am able to take some samples, right? Taking samples is going to be expensive and I can't take too many of them. But the idea is exactly like in the microservices system, the load will change over minutes and hours, right? It won't change too much over minutes, it will definitely change over hours. So you can think of it as the f is really changing every couple of hours or every 2-3 hours, right? So it's changing slowly, but it is changing. But I'm allowed to take a bunch of samples. And so basically my algorithm is going to take those samples efficiently, hopefully, and it will compute an estimate of the gradient, right? And then based on this gradient, it will change the allocation, right? And so on. So in other words, this algorithm has two portions. One is trying out different values of x to get samples. And then the adversary changes the function and so on. So effectively, the question is how many samples do I take? How do I use them effectively? That's the high level problem. So I need to do gradient estimation with a limited number of samples. Now, these are called, some of these gradient estimation methods are called zeroth order methods. Zeroth order simply means that I perturb it, f of x plus delta minus f of x by delta kind of estimate kind of things. So the trouble is that, as I said, in our microservices case, the number of dimensions is enormous, right? 50, 100, maybe even more. And so sampling every dimension is impractical. You can't possibly keep all the other containers fixed, tweak one container, take some measurements, then tweak another container, take some measurement, tweak another container, take some measurement. It's just impossible. So sampling every dimension is impractical, right? And indeed, if you did, you would need, D is the dimensionality of the system. So in this case is the number of containers or number of parameters I am allowed to choose. There's a result which basically says that if you want sublinear regret, that is, if you want the regret to scale, regret by time to decay, then essentially you need D plus 1 samples. So in other words, you need a dimensionality worth of samples, right? Now, the thing is, there is another approach which was originally introduced by Spall called simultaneous perturbation stochastic approximation. It is a way of essentially a kind of low-cost way of obtaining nearly unbiased gradient estimates, which uses two function evaluations. So in other words, what you do is you take f of x plus delta minus f of x minus delta divided by delta as an approximation, right, in an interesting way. Now, the problem is it has a fairly high variance. And so when you do this over and over again, remember in my online convex optimization, it is not one f. The f is going to keep changing. And so basically, the error will build up if we don't do anything clever. So that's a problem, but it's a good way to start. Now, one thing that helps us is the following. So in queuing networks and many kind of common problems, particularly in large scale kind of optimization of compute systems, the number of containers or number of queues which are bottlenecking you are relatively small, right? So for example, what is mentioned here is the reasons for a particular queue not influencing the latency is that there's nothing much going on in that queue. There's either few jobs in that queue, it's not much used, or it's not this queue which is the problem, it is something else which is the problem. There's a downstream bottleneck. So in other words, when I think of this 50 container system, most of them are probably okay, right? Only a few of them are likely to require modification. So in other words, the number of these parameters which lead to appreciable gradient is fairly small. And here is a measurement in this container system. I'm looking at, essentially the gradients, negative gradient. Basically, I'm trying to look at what causes latency to fall down. So I'm basically pointing out that these are of interest. So we ran it for various different workloads, and we found that most of the gradients are kind of, are not making, they're kind of centered around zero. So there's not much going on. But you see distinctly a few containers are the ones which respond well. So in this particular case, what we did was we actually bench tested. We ran the application And we basically said to modify this one, modify that one, modify this one, modify that one, while keeping all the others fixed. And we found only a few containers are really the dominant ones, right? So in other words, in this example, the gradient is actually sparse. Only a few gradients are non-zero, or at least, if you say all these are zero or not worth touching, you can argue that only a few of them in this particular workload, only these three are worth touching, these four, etc. So only a few containers are problematic at any particular time. So this is the notion of sparsity. So I basically took my talk and gave it to Google Gemini yesterday, and I got some pictures out of Gemini. So Gemini basically says that this notion of sparsity is trying to find a few discordant instruments in a whole orchestra of instruments. So essentially the idea is that there is a whole bunch of dimensions. Only a few dimensions are relevant. But what I'm hearing is the combination. I'm measuring end-to-end latency. So the question is, how is the person sitting in the box to identify the three discordant instruments from the whole, right? Now, so basically, what we really desire, therefore, is to develop these zeroth order methods. In other words, methods which are modifying the argument of the function. As I said, it looks like f of x plus delta minus f of x by delta x by delta to kind of estimate the gradient, right? So what do? We're going to basically develop this gradient estimation method that uses compressive sensing for this OCA, right? What we want is ideally sublinear regret, and you can get sublinear regret, we also already know, because if you get d+1 samples, you can get it. You'll have to measure every single instrument here, right? D is basically the number of instruments here. So if you want to get sublinear regret without exploiting sparsity, you need to take as many samples, order of, as the number of dimensions. Whereas what we want is dimension independent sublinear regret, ideally, right? That's what we want. Okay. Hopefully the problem is clear. I want to spend a little time on what is the definition of sparsity and what we're going to do. So the sparsity is basically saying that essentially, if you take the support of the dimensionality, so we basically the support of the gradient. Essentially, the idea of sparsity is that the support of this vector is less than or equal to s. All this is saying is that if you have a vector of size d, essentially most of the elements of that vector of dimension d are zero, and only a few less than or equal to s are non-zero. Right? Now, this is approximately sparse in our problem. In other words, you saw that if you have like 50 odd containers, maybe 3 or 4 have a non-zero gradient idea, approximately. So now compressive sensing, basically what it does, it basically takes measurements which are linear combinations of these x's. So it looks like, for example, I'll just show you how a sparse measurement is taken. But essentially, the idea is that that effectively essentially what you get are AZs, right? And what you want to recover is X. So essentially, so what is really going on in the compressive sensing case is actually that I take that back. Sorry, you get measurements of the form AX. You take something called a measurement matrix. That's A. X is the dimensionality of what you're trying to measure, and you know that most of the x's are zero, only a few of them are non-zero, right? So what you do is, instead of measuring x directly, you somehow manage to get AX, right? So AX, basically what you're saying is you can mix and match how to combine these x's. In that instrument case, I can say, I want 3 violins, 4 tubas, and whatever, right? That's the kind of thing that this A gives you. It gives you the ability to kind of additively combine these measurements. So you get a bunch of combined measurements, and what you want to do is recover. That recovery is the Z. So what you're doing is you're trying to recover a small number of assuming that the x is not, assuming that the support of x is relatively small, you basically can recover a small number fairly effectively, as long as this measurement matrix, as it's called, measurement matrix A, has the so-called restricted isometry property. So the measurement matrix, the restricted isometry property, is kind of visible here. Essentially what it says is that x and AX, their norm should be very similar. So isometry means distances are the same. So effectively, if you look at x, the domain of x, You look at distances, say whatever norm you're looking at, 2 norm, 1 norm, whatever you're looking at, and you look at the AX and the norms in both of those spaces, if they're very close to each other, it says delta is less than 1/3. If those norms are very close to each other, you say that the matrix has the so-called restricted isometry property, right? So that is going to be important. It's fairly easy constructing matrices which have this. You basically Gaussian matrices have this. But the point I'm making is that essentially certain random matrices have the restricted isometry property and therefore are capable of compressive sensing. Okay. So this is really what I was talking about. This is again a Gemini generated image. It basically says that the purpose of compressive sensing is to carefully combine these instruments, so to speak, linear combinations of these instruments. That's the A matrix. And you get samples which are such linear combinations. And then you filter them out, right? That's where this AZ equals AX kind of thing comes in, to actually find out what the X's are, what the small number of in this case, out of tune instruments are. That was the general idea. Okay. So if we want to do compressive sensing, it's all very well. You'll get AZ equals AX kind of thing. But I want to use compressive sensing for gradient estimation, right? I'm not interested directly in an AX equals AZ. I want the del Fx. In other words, what I want is not an X kind of thing. I want a del Fx. You notice this is of exactly the same form that we saw earlier, A times something. But that something, as I said, is not X. It's the measurements I'm trying to take, or what I'm trying to estimate, are gradients across many dimensions. Okay. So really, I'm trying to look for noisy, compressed gradients. That's the kind of samples I'm trying to recover. So in other words, I'm not going to just try to, so what I need to do is I need to somehow come up with some way of measuring samples of this kind. So what we do is the following. So the first thing you do is you generate a perturbation. So what essentially you create a so-called perturbation matrix in this case, right? And what you're doing basically is you're adding this perturbation. This is actually the capital delta is a vector, and so you're perturbing each dimension of x, right? By a certain delta. These deltas are going to be randomly drawn. And so you take estimates of this form. This is what I meant by saying f of x plus delta minus f of x by delta is basically the definition of the gradient, approximately. It's approximate because essentially this is del f by del xi, but because I've kind of perturbed a variety of dimensions, you'll get some additional terms as well. You'll get this is a Taylor series approximation of this quantity, right? Really, if I were to let limit delta go to 0, then these might wipe out. So you want to take small deltas, right? But if you take any appreciable delta, you are going to get some error, right? So essentially what we're saying is that you can say this is just the same as the previous one there. This is f of x plus delta basically. Delta is the size of the perturbation, and this delta is which elements are perturbed together, right? So you're perturbing a variety of dimensions. Those dimensions are perturbed by little delta, right? So essentially what this yields is it gives you this kind of inner product form that we want, which is the inner product of the gradient with the perturbation, and you get noise. Now the point is this noise better be bounded. In this case, it says that the noise is less than a certain variance term. So you want to basically make sure that you give me, or you pick enough samples that this noise is limited. So essentially, what is this noise? What is its variance? That's the kind of thing we're interested in. How much noise does it cause, right? So basically what typically is done, right? I mentioned that this is the perturbation vector, right? Think again now. Let's say my x is of 3 dimensions, 1, 2, 3. So then essentially what I'm doing here is I'm choosing which of those x's to perturb. Maybe I perturb 1 and 2, maybe I perturb 2 and 3, maybe I perturb 3 and 1, or just one of those dimensions. Any of those are up, fair game, so to speak. That is these perturbation vectors. To create such perturbation vectors, what you typically do is you take what is called a measurement matrix A, and essentially this perturbation vector is basically A transpose delta of this form. So essentially what you're doing is you take this matrix. The simplest way to think about it, and this is what ultimately we do, each row of A will go into the kind of think of A as M cross D, right? D is the number of dimensions. So in other words, what is going to happen is if your A has D dimensions, think of each row of A as picking out which of those dimensions you're perturbing. That is the interpretation we are saying is a good idea. Now, mind you, the result basically says that you can take any arbitrary kind of A subject to certain conditions, Gaussian matrix and so on, and you can convert that matrix into a perturbation vector. If you essentially you can then take that perturbation vector, perturb those dimensions, right, in a certain manner. J equals 1 to m a delta a j, it says. So effectively your A matrix is m rows and d columns. So you can combine in any weird way you want. That's what this is saying. You can combine in some weird way, and then you basically take a gradient estimate. Now the combination you choose, the A matrix you use and the way you combine it will give you your errors. So in other words, what we want is to create these matrices so that we have good gradient estimate which have low error in them, and then show that that the regret bound is relatively low, sublinear basically, when we use such gradient estimates. So we need a bound on the error that that essentially to have a bound on the regret, we have to have a bound on the error of the gradient estimates, right? So we want to basically bound the bias, which is the difference in expectation, and the variance. Those two I need to do. So our method, again, Gemini image, is basically the following. We have to first generate this matrix, this measurement matrix, in a kind of clever manner, right? And that's what I'm going to spend the next slide or two talking about, how these matrices should be created. Now, using these matrices, I can collect data. Again, each data sample has to do with perturbing some number of these dimensions and getting an additive kind of difference, basically the f of x for that perturbation. Again, in my microservices case, what I would do is I basically decide which of these containers I am going to change. So I make some tweaks to their CPU allocations. I'm going to measure end-to-end latency. That gives me one data sample. So I'm going to get several such data samples. I collect such data. These are compressed kind of samples basically. I recover the gradient. This recovery process is essentially an optimization problem, right? So I use compressive sensing to kind of recover these, and then I basically do an allocation, and then I repeat, right? Allocation means I change the CPU for allocation for each one, and then I measure again. Okay, so this is again the same thing. First, I have to generate a measurement matrix, this A matrix, right? I need to ensure restricted isometry because I'm going to ultimately do compressive sensing. So once I choose my A matrix, I'm going to perturb some dimensions, the dimensions as suggested by A, right? Each row of A is what it will turn out to be. Then once I have got my perturbed samples, I'm going to basically compose these to get essentially measurements. These are basically effectively these kind of inner product type thing is what I'm interested in. Basically, I'm going to take f of x minus f of x plus delta minus f of x by delta kind of stuff. So I'm going to basically get these measurements, right? And then I'm going to kind of recover a sparse number of gradients using this. So essentially, there's going to be a constrained recovery process. If you remember a couple of slides back, I said we're going to solve under a constraint that az equals ax, minimize the number, the norm of z. In other words, I'm going to say, I want to recover no more than a certain number of gradients, solve it as best as you can, and it will produce basically gradients for all of them, but only a small number of them will be accurate values. The others are basically meant to be zero. So and then we do a gradient descent update step. We use that gradient to say, okay, these are the microservices, these are the dimensions which I need to change. I modify the allocation there, then I start again. Okay. So this measurement matrix is a very important element, and we have a variety of these the kind of variants on this algorithm. So the first thing is, how do I create this A matrix? As I said, A is this measurement matrix. D is the dimensionality of my problem, the number of microservices or number of parameters I'm allowed to choose. M is basically the number of measurements I'm going to take. That's why it's an M cross D matrix. So that's why I said think of this A matrix as being vectors of length D, vector 1, vector 2, vector 3 of length D. image in mind. And essentially, the kind of as I said, you can actually combine these measurements in any which way. But the way we like to think about it, which turns out to be the right way, is that each row of this measurement matrix of dimension d is supposed to produce one measurement sample, right? It turns out that is the right way to think about it. So basically, this is what I'm talking about. I want a measurement matrix where each row AI corresponds to one such desired measurement, right? If we do the combinations this way, we can bound the error very nicely, right? So although the SPSA algorithm suggests that you take a measurement matrix where you can combine, essentially all the dimensions in some weird way, it turns out this is a good way to actually bound the error. So effectively what we're doing is this delta, remember this delta vector was what multiplies the x. Essentially, I am going to choose a certain set of x's which I'm going to combine, and those are contained in the AI. So in other words, these AIs will be either zeros or ones, and I'm going to take, if a particular AI is a 1, it means that particular dimension has been selected for perturbation. The amount of perturbation is delta by the norm squared of A. This will take care of some of something which will cancel out later. But really we're saying this delta chooses which of them I'm going to simultaneously perturb, right? So basically, the algebra basically says that what I'm going to do is I'm going to basically choose the dimensions to perturb effectively, right? I perturb those dimensions. Again, x is a vector, delta is a vector. So I'm going to basically perturb some dimensions. I'm taking the difference of this. Then the Taylor expansion will give me this inner product that I'm interested in, plus some noise, right? And so essentially, if I divide by this delta by a squared, I will get a noisy estimate of what I'm interested in. So yi will be a noisy estimate of grad f times ai plus ei, right? So it basically then it gives me a measurement of the form I'm interested in. Now there are other ways. If I use more complex matrices, I'll still get this form, but I'll get additional error terms, right? Professor Vivek Borkar from I guess TIFR IIT Bombay, he had an interesting work earlier on essentially convex optimization. It wasn't an OCO problem; it was a fixed function. And he had an interesting paper where he wanted to, or he proposed using simultaneous perturbation. They had used kind of arbitrary these matrices, and it turned out that they have extra error, which causes the regret to grow in a manner that we don't desire. In other words, you need a lot more samples to get sublinear regret with that. So we were inspired by that algorithm. Then we realized that for our OCO problem, we want to construct these measurement matrices much more cautiously, and so that's the version that we call CONGO B stands for Borker's algorithm, and we came up with more efficient versions which are more conducive to online convex optimization. So the first result that we have, I'm going to go quickly through the analytical results. So the first result that we have basically has to do with this error. You notice what I'm interested in. You can forget all the other stuff on the slide. Essentially what we're interested in, y equals a del fx plus e. How much is your e? That's the big question. So we're basically saying if you construct it with row by row perturbations of this matrix, you're going to get some error which is reasonably bounded by a kind of square root m, right? Whereas if you have other constructions in which, for example, you have random Rademacher random variables plus 1, 0, 1 random variables kind of thing, then you'll get more errors, which is problematic. So really, we want to stick with one which has smallest error in our gradient estimates. Good. So a few subtleties according to the usual compressive sensing, and it actually applies in socio context. You can actually take a single measurement matrix and you reuse it all the time. But if it has, if that particular sample was bad, then it's going to mess up your entire OCO problem. So we just sample a new matrix for each time. So basically, we basically ensure that this matrix is sampled every time. Now, the number of rows of A, I mentioned, the way we think about it, it's M cross D, remember? D is the number of dimensions of the problem, and M is essentially the number of samples you're getting. So the failure probability needs to decrease as the horizon increases. So the number of rows needs to increase. So, but you don't want to increase as D. So it actually turns out it's only logarithmic in the dimensionality of the problem. So it's relatively easier to deal.
Excuse me, Professor, I have a question.
Please.
In choosing of this matrix, measurement
Mm.
matrix A, you need to know the sparsity level.
Yes.
So the gradient you need to know like in your network like how many bottlenecks are there.
Correct.
So how do you because
use an
only
upper
then
bound. Yeah.
Okay.
Good point. So essentially, we're saying that what I'm interested in at each time is trying to find my top 5 or top 10 things, right? Mind you, it's not like I'll get 0 as the other answers. I will get the whole thing, right? When I solve for the thing, only S number of them are valid in some sense. You're trying to solve because what you do is you minimize norm Z subject to AZ equals AX, right? So essentially, the dimensionality of what you get will be accurate only in the number that you solve for, and that number should be close to what you're looking for, right? So yes, you'll only get reasonable accuracy if your sparsity value is not too different from reality. That is correct.
Thank you, Professor.
So here is the algorithm. First thing is create a measurement matrix, right? In this particular case, I'm using a measurement matrix with Gaussian entries. It turns out these Gaussian matrices have a good restricted isometry property. Then essentially what I do is I take each row of this and I basically do my perturbation with that. Then I construct these Ys, these kind of gradient, noisy gradient estimates with that. Then I basically solve. This is what I was just mentioning. It's a constraint gradient recovery. So we use different algorithms. There's one called basis pursuit, which is a bit slow. COSAMP works a little better. They have certain good analytical properties. We assume that you can solve this efficiently, which COSAMP does for us. So therefore you solve for the gradients and then you apply the gradient. This is just ordinary gradient descent. So essentially you're pretending that your gradient estimate is the true gradient and you basically just do gradient descent. And then you kind of repeat and your total regret is this, right? So the two elements, as I said, is choosing this matrix correctly, right? And of course, then of course, composing them so on. And the regret bounds are how many M's, how many samples do I need in order to get a sublinear regret, right? So essentially what we're saying is that if basically we are looking at a sparse problem, then the essentially basically the regret of the algorithm would basically scale a square root t as long as your gradient estimates are not too bad. So this theorem 1 basically says that as long as my gradient estimates don't scale too badly, m is essentially the delta is the amount I chose, and m is basically a parameter which depends on my sample number little m. So capital M is related to little m basically. So effectively it says as long as your gradients are not too bad, right? This needs to go down nicely, right? Then basically I will end up with square root t regret. The other part is how do I make sure this happens, right? With the number of samples that I have. So essentially the lemma 2 has to do with this notion of being able to bound that gradient, right? Notice that here I need this bounded gradient and I need a bounded 2 norm of the gradient as well. The question is, how am I going to make sure that it's bounded? I need to take samples. How many samples do I need to take? Well, so it basically says, this is actually a result which we found from Foucault on how big the M must be, right? So essentially what it says is, if you're doing these kinds of kind of gradient estimates, it's slightly different in Foucault's case, but it was essentially a kind of gradient estimation type problem. So it says basically that if you're trying to ensure that you have bounded gradients, you can do it as long as the number of samples is big enough, right? So essentially, you notice that it is logarithmic in the dimension d. It is log d by s. So it is linear in the sparsity and logarithmic in the dimensionality. So effectively what we're saying is it is feasible to get these to work out with small enough kind of error in the gradient as long as your m is big enough, the number of samples. So in other words, again, think of your measurement matrix. Again, measurement matrix, the number of columns was d, number of rows is m. Each m is one sample. right? So effectively, the number of samples you need is not terribly large. That's what it says. So the general idea is basically that lemma one, which we looked at just now, basically gives a kind of error bound, and then we convert the measurement error into a recovery error kind of thing, right? And then what we need is essentially a bounded gradient estimate, right? That's what will give us the regret bound that we want. And essentially these two together give us the right number of samples that we can get a bounded regret bound. So together, when we put everything together, what we get is for this variant in which we chose those measurement matrices in which each row contains the kind of dimensions to be combined, we find basically these are called CONGO Z and CONGO E. CONGO E stands for efficient CONGO. Z stands for a version which we picked up, a variant that we saw. There was an algorithm called Zoro, which does this notion of looking at samples drawn from row-wise as opposed to matrix-wise, right? And B, of course, is the Borker approach, which takes this measurement matrix where you combine all the elements of the matrix. So anyway, the point we're trying to make is these more efficient versions where you choose that A matrix nicely basically have essentially the number of samples is S log D kind of thing, right? And it scales logarithmically in the total time that we need. Remember, this is OCO, so I have to do it round by round by round. So in other words, based on the number of rounds, you need more samples, but it's again growing logarithmically in number of rounds. It's growing logarithmically in B and linear in S, right? So essentially, the regret bound for all of these follow in similar manner by ensuring again both the bias, the error in the gradient, and the bias variance have to be bounded. That's really what we do. Okay, so that's the analytical results. Now the question is, can we actually utilize this in simulation, and can we do it in a real system, right? So what we looked at here are basically the accumulated cost, effectively the overall regret for a variety of algorithms. So just plain old gradient descent, etc. So essentially these CONGO versions are these down here, and we find that the gradient is actually looks pretty good. The kind of overall regret accumulated cost looks pretty good for these more efficient versions of CONGO. So you notice the accumulated regret is falling quite quickly, right? So we did some work on a Jackson network as a kind of this was a Python simulator. Jackson networks are recurrent queuing networks. You go to one queue, then go to the next queue, then go to the next queue, etc. With some random matrix which tells you which queue to go to next, right? And these Jackson network application kind of experiments were all pretty good. So effectively, we were saying that the cost, the overall latency of the system does fall quite quickly. The baselines we were looking at were different kinds of gradient descents. Gradient descent with simultaneous perturbation, for example, right? It doesn't do so well because after a while it starts being able to find the gradient, but really the rate at which the kind of cost falls is much better for the compressive sensing type approaches. And indeed, it falls quickly and stays pretty low. Then finally, we did the actual real world application in which we took a benchmark application. In this case, the one shown has 26 microservices. And what we did is to get a good baseline, because we don't know the actual cost functions, we trained an RL agent using PPO to choose the appropriate allocation in which you know the workload. In other words, this is not feasible in reality, right? Because we basically said let the agent actually know the workload, but it gives us a kind of lower bound on what might be possible. So that's it's a kind of optimal should be in quotes. We don't know what is actually optimal, but we use this so that we give you an RL agent which knows more than what reality actually gives you. And here that's this baseline down here. This is the RL agent which is kind of all-knowing, so to speak. And again, we tried a variety of these CONGO type algorithms as well as regular gradient descent, and gradient descent with simultaneous perturbation and so on. You do notice, I mean, all of them do reduce the overall cost, but you notice that the CONGO E, the efficient versions, which are doing these perturbations carefully, do indeed kind of give you the best performance. And in this case, there was variable arrival rates. These little lines show you when the arrival rate is changing. And we're trying to see kind of, does it track well enough? It seems to be reasonable. It basically goes up and down a little bit. But these CONGO variants do at least try to keep the overall cost low even when the kind of arrival rates change. In this particular case, the arrival rate you notice is it decreases for a bit, then increases, then increases and goes up again. But in spite of that, the cost is held relatively low, right? So that's essentially what we're saying, that it is feasible to actually deploy or these kinds of sparse online convex optimization style approaches to kind of resource allocation. It allows us, I mean, finally, the kind of main takeaways are choosing this compressive sensing matrix, the A matrix, correctly enables us to basically ensure the number of samples is small enough that we can get good regret bounds. Basically, we can keep the bias and variance bounded. So we're able to get the sublinear regret bounds without having a dimensionality too high. So the main takeaway there was that we can get the number of measurements being proportional to S, the sparsity, instead of D, which is the dimensionality. And instead it becomes logarithmic in the dimensionality. And of course, it was logarithmic in the total time. So that's the general kind of idea. So and we were able to show that it's actually empirically, it actually works reasonably well. So we're looking at variety, kind of variants on this, meta learning with this, where essentially the microservices might change over time and things like that. But this was the kind of fundamental idea in this paper. Thank you very much. Let me stop sharing so that I can see better. And then any other questions, thoughts, or comments?
Thank you, Professor, for accepting the request and delivering an interesting talk. Yeah, we have a question.
Excuse me, Professor. I have two questions. Can you hear me?
Yeah.
So the first question is that in your last experiment on real-world networks, how do you estimate the sparsity level in that you have 26 microservices, and how did you estimate, and how do you choose your measurements in that real-world setting? Because in your previous experiments, you've set sparsity level equal to 5, but in your last experiment, I did not see it like, oh, what is the sparsity level? How do you estimate it?
So we did some idea. So we ran a few experiments. I mean, we did some initial measurements to see how many of these microservices, the first graphs that I showed you, we looked at the gradients to get an estimate of in this particular application, what is the kind of bottlenecking that is going on in practice, right? So that's how we found that. So we did do some bench testing, so to speak, for an application as a whole, to see typically what kind of bottlenecks happen in this.
And the second observation is that in your plots, I noticed that you have lower variance for the CONGO algorithms when you have the variable load. In the three plots that you've shown with variable loads, fixed load, and variable arrival rates, the variances are more for the variable loads, but variance is low for the variable load.
The axis is compressed. So essentially, if you look at the variable load, it has already learned more or less what is the right thing to do. And so it's not changing that much, right? So in spite of the load, in fact, we first time we did the experiments, we were looking at load just continually decreasing. There it doesn't matter, essentially you found the bottlenecks, you already know what's going on. But essentially, even with variable loads, we did go up and down with the loads, but the overall cost has pretty much already converged. So it's not, in fact, if you notice, even the RL baseline was almost flat with the variable loads. Basically, it means that with the variable loads, essentially the cost had the kind of overall cost of the system was kind of well under control, so to speak, right? So effectively, the learning was over, as it were, fairly quickly, in spite of the load going up, right? That's really what happened there.
Okay, thank you.
Thank you for the question. That was good. So any other comments or thoughts that folks might be interested in? Good. So what do we do now?
Thank you everyone for attending. Thanks again, Professor. I'll end the call. Yeah.
Thank you so much. Thanks, everyone. Bye.